Hey there and welcome. Today we're putting together the ultimate playbook, kind of like a last-minute revision guide for one of the most foundational ideas in all of machine learning, generative models. We are going to build this thing from the ground up, so by the end, you'll know exactly how these models tick.
Okay, so here's the game plan. First up, we've got the foundational fork. This is the big initial choice you always have to make. Then, we'll dig into the full story to see what a perfect ideal model would look like. Spoilers, it gets complicated. So next, we'll learn the clever shortcut that makes everything practical. And to make sure it sticks, we're running the drills. And then we'll wrap it all up by making the final play to see how it works in the real world.
So let's kick things off with that first play, the foundational fork. To really get what a generative model is, you first have to understand what it isn't. And it all boils down to this one fundamental choice you have to make when you're tackling any kind of classification problem.
And this right here, this is the core difference. Think of it like this. On one hand, you have discriminative models. All they care about is drawing a line in the sand to separate the groups. They're trying to learn the probability of the label Y, given the data you show them X. But then, you've got generative models. These are, well, a lot more ambitious. They don't just want to draw a line. They want to learn the entire story of how the data was created. They model the joint probability of X and Y happening together. It's a total shift in perspective.
Right, so a generative model isn't just a simple predictor. It's really a storyteller. It builds this little narrative in its head. Imagine it like this. First, the model flips a weighted coin to decide on a class, say spam or not spam. Then, and only then, based on that outcome, it starts generating the features. The actual words that would appear in that kind of email. So let's see what it takes to actually model that full story.
All right, let's dive into the full story. Let's imagine for a second that we want to model this generative story perfectly. I mean, no shortcuts, no assumptions, just the pure, unadulterated process. What would that actually take? Well, as you're about to see, this ideal world approach gets really, really complicated fast.
So it's basically a two-step dance, just like the story we talked about. Step 1, you figure out the odds of picking any given class. That's your P of Y. Step 2, once you know the class, you figure out the odds of generating the specific data points for that class. That's P of X given Y. Sounds pretty straightforward, right?
Well, let's actually put that to the test. Let's get our hands dirty with a super simple example. Imagine we have a tiny problem, just two classes. We'll call them 0 and 1. And our data has only 3 binary features. So each feature is either a 0 or a 1. Now the big question is, to model this thing perfectly, how many different probabilities or parameters do we actually need to learn from the data?
Okay, let's break it down piece by piece. First up, P of Y, the probability of the class. Well, there are 2 classes, so we only need to learn one probability, right? Because the other is just 1 minus that. So that's one parameter. Easy. But now for P of X given Y, things get hairy. With 3 binary features, you have 2 times 2 times 2. That's 8 possible combinations of features. And we need to learn the probabilities for all of them for each class. So for each class, we have to learn 7 parameters.
So let's add that up. You've got the 1 parameter for the class, plus 7 for the first class, plus another 7 for the second class. That is 15 parameters. 15 for a ridiculously tiny problem. Can you imagine if you had 100 features? The numbers would just explode. So yeah, this perfect approach is powerful, but it's just way too complex and needs a ton of data. There has to be a smarter way to do this.
And of course, there is. This brings us to the hero of our story, the clever shortcut. This is the absolute turning point. We're about to introduce one simple, powerful assumption that makes this whole generative model idea actually work in practice. This is the key play in the entire playbook, and it's what gives the famous naive Bayes algorithm its name.
So what is this brilliant shortcut? We're going to be a little bit naive. We're going to make a big assumption. We're basically going to pretend that once we know the class, say we're generating a spam email, then the chance of seeing the word money has absolutely nothing to do with the chance of seeing the word win. We're just going to assume that all the features are independent of each other.
So the fancy term for this is class conditional independence. And what it means is that instead of trying to model the probability of that one huge, messy combination of all the features happening at once, we can just look at each feature one by one. We find the probability of each feature given the class, and then we just multiply them all together. It's a total game changer. It makes the math so much easier.
Now let's look at the math again with this assumption in our back pocket. The P of Y part, that's still just one parameter, no change there. But for P of X given Y,
Wow, we don't need to worry about those 8 combinations anymore. We just need to learn one parameter for each of our 3 features for each class. So instead of 7 parameters per class, it's just 3.
So what's the new total? It's 1 plus 3 plus 3. That's only 7 parameters. We went from 15 all the way down to 7. We literally chopped the complexity in half, just with one naive little assumption. And that is what makes the naive Bayes algorithm so incredibly efficient and honestly so powerful.
All right, we've got the core play down. Now it's time to lock it into muscle memory. We're going to run some drills. Let's tackle a quick practice problem to make sure we can apply this playbook when the situation changes a little bit.
Okay, here's the drill. Let's switch it out. This time, you've got a 3-class problem. Let's say classes 0, 1, and 2. And you still have 3 binary features. So, using our naive Bayes playbook, how many parameters are you going to need to learn? Think about it.
Let's break it down together. First, the class probabilities, P of y. With 3 classes, we only need to learn 2 of the probabilities, right? Because the third one is just whatever's left over. So that's 2 parameters right there. Now for the features. We have 3 features, and we need to learn their probabilities for each of our 3 classes. So that's 3 times 3, which is 9 parameters. Add them up. 2 plus 9 gives us a grand total of 11 parameters. Not bad.
Okay, we've built the model, we've run the drills. Now it's time for the final play, the moment of truth. Let's see how all this theory and math actually comes together to make a prediction on a brand new piece of data it's never seen before.
So imagine this is our trained model. We've already done the hard work of learning these probabilities from a bunch of data. So for example, we know that the chance of feature 1 being 1 if the class is 0 is 0.2. And we have all these probabilities for our 2 features across the 2 classes.
Okay, now a new data point shows up. Its features are 1, 0. And here's the twist. We're told that our model looked at this data and predicted it belongs to class 0. So the question is a bit of a detective problem. What must have been true about our initial guess for the probability of class 1? We're basically working backwards to figure out the limit on py equals 1.
Remember, to make a prediction, the model calculates a score for each possible class, and it just picks the class with the highest score. And that score is super simple. It's just our prior belief, P of y, multiplied by the evidence from the data, P of x given y. So since we know the model picked class 0, it's a no-brainer that the score for class 0 had to be bigger than the score for class 1. Now, let's plug in the actual numbers we have.
All right, let's do the math. Just to make it simple, let's call the probability of class 1 p. That's our unknown. So the probability of class 0 is just 1 minus p. Now let's build those scores. For class 0, the score is 1 minus p times 0.2 times 1 minus 0.5, which simplifies to 1 minus p times 0.1. For class 1, the score is p times 0.6 times 1 minus 0.4, which works out to p times 0.36. We know the class 0 score is bigger, so we set up the inequality, do a little algebra, and we find that p has to be less than about 0.217.
So what does that number actually tell us? It means that for our model to choose class 0, our starting assumption, our prior belief that something belonged to class 1 had to be pretty low. It had to be less than roughly 22%. And this is a perfect example of how naive Bayes works. It's a team effort between your prior beliefs and the actual evidence you see in the data. They both work together to make the final call.
And that leaves us with one last big question to chew on. We've seen just how powerful and efficient this naive assumption is. It's a fantastic shortcut. But when is it a bad assumption? What happens when our features are obviously not independent, like the words San and Francisco? When could this shortcut actually lead our model down the wrong path? Thinking about that trade-off, well, that's the next level in really mastering these models. Thanks for sticking with me on this one.